We're going to talk about lightning and thunderstorms and tornadoes. So a whole bunch of things that we very, very rarely see over here in our perfect little climate by the sea. But especially for those of you that have lived inland at all, either sort of locally or even further across towards Texas, parts of the Midwest, then you are used to experiencing much more severe weather than we have here. And because I think it's much more exciting to watch severe weather than just hear about it, I have a lot of videos today. So bear with me, but they should be fun. So, Lecture 14, Lightning, Tornadoes, and Thunderstorms. Let's continue with a little bit of a review. Because what we did on Thursday was actually really challenging. I think it's the most challenging thing we do in this class, because there's, again, a lot of steps to get to the particular answer that we're looking for. So I want you to look at my top diagram to begin with, my top right-hand side diagram. And what that is showing you, that little loop, is showing you what the upper level winds are doing. They are looping from sort of position 1, which is closer to the pole, and they're looping sort of closer to the equator, up high in the atmosphere, and then back again. So they're staying at the same altitude in the atmosphere, they're just changing from closer to the pole to closer to the equator and back. Okay. So as we go from 1 to 4, we're going from closer to the pole to closer to the equator. What happens to my planetary vorticity as that happens? Does it increase or decrease? It decreases. And so if my absolute vorticity has to stay the same, what happens to relative vorticity? Increases, absolutely. We're going to increase our relative vorticity. And how did my friend on the chair do that? Did he throw his arms out, or did he pull everything together? Everything together, just like the ice skater went round faster and faster. And so what we have is all of those air molecules at that particular point, at say from 3 to 4, we're sort of constantly decreasing our vorticity as we go from 1 to 2 to 3. And so our relative vorticity has to increase. To do that, we converge air. All of those air molecules move together and get packed tighter together. And that means that we're not going to keep those air molecules packed tightly together. They're going to move. We've created a high pressure. And they're going to move down to the surface. And we're piling air back down to the surface. And so we're also going to create a high down at the surface. Okay? If we look at what happens between 4 and 6, we have this constant amount of relative vorticity. And now we're not going north-south anymore. We're really just going along. Okay, so we're not really changing anything. But after a while, from 6 to 7, then we start going north again. We're moving closer to the pole. So what is happening to our planetary vorticity? It's increasing. So what happens to has to happen to our relative vorticity? It decreases. And so how did we decrease our vorticity? We spread out. Okay? And in that case, we're diverging. All of those air molecules in that upper wind there are diverging. We're not going to end up with nothing in the middle. That sort of diverging in the upper atmosphere is going to pull up air molecules from underneath. And so if we're removing more air molecules from the surface, we're going to create a low underneath that diverging air. And so that's why we get these highs and our lows. And this is what, when we created, or when we didn't, when Bjerknes created his polar front model of how these cyclones sort of develop, he didn't really know about what was happening in the upper atmosphere. And so he couldn't explain exactly why that was forming. He could describe it, but he couldn't explain it. And it really is sort of knowing what these upper level winds are doing, these jet stream winds, that help us work that out. Is everyone okay with this concept? Yes? No? Ask me again in 3 weeks when you're studying for the final? Yes? Okay. So, in that case, let's move on and start talking about electricity and charge in particular. So, as a very quick reminder, I don't want to insult your intelligence, but I know that it's been a while since some science classes at school. So remember, the atoms are the smallest individual particles that retain the properties of a given substance, chemical element. And those atoms are made up of protons, neutrons, and electrons. The protons and neutrons have a mass unit of 1, and they sit in the nucleus. The protons have a plus charge. They have a +1 charge. The neutrons are neutral. They have no charge. And then around that central nucleus, we have these electrons orbiting around. And those electrons don't have very much mass, but what they do have is a negative charge. They have a negative sort of -1 charge, okay? So when we talk about ions, what we're talking about is a charged atom. So it either has an extra proton or an extra electron, and so it has a charge to it, okay? And we have certain rules that govern how charged things behave. So that should say charges rather than changes, like charges repel, opposite charges attract. So just like when you played with magnets when you're a kid, you have two north poles, you can't get them to stick together. You need a north pole and a south pole to stick together. It's the same thing for positive and negative charges. Two positive charges won't stick together, but a positive and a negative charge will. The bigger the charge, the stronger the force. That's not surprising. The closer the ions, the stronger the force. So the closer they are between each other, the stronger an attraction they feel. And so my example here is electrostatic induction, and you have all done this at home. Does anyone know what I'm talking about? Balloons. Who has taken a balloon and rubbed it on their friend's head or their sibling's head and tried to stick it to a wall? Yes. Okay, at least a few of us. If you haven't, why not? So that's your task for the weekend. And what you'll find is that balloon will stick, and it works especially well in the really dry weather here. Okay. Also, if you have a pet and they run across the carpet a lot and you touch them and you get a little bit of a shock, it's electrostatic induction. So let's talk about lightning, because lightning is this movement of charged ions. And when we think of lightning, we think of the classic lightning strike, which goes from the cloud to the ground. But actually, the vast majority of lightning strikes that happen don't actually come anywhere near the ground. Most of that lightning, 80% of it, actually occurs within the cloud itself. We don't necessarily see it. And so especially, have you ever been on a plane flying past a thunderstorm and you see little flashes within the cloud? Yeah, a few people have. It's a bit scary to be that close, but yes, you can see that those lightning strikes are within the cloud as well. Only 20% of them actually go from cloud to the ground, okay? And so what we're doing when we have these lightning strikes is that we have an electricity discharge. We have this movement of electrons between the cloud and the ground or within the cloud itself. So let's think about our steps of lightning formation. And I'm going to preface this by saying that there is so much that we have absolutely no idea about when we're talking about lightning. It's a really not terribly convenient place for lightning. It's not an easy thing to study because it happens very fast, it happens in somewhat random locations, and you don't want to be terribly near it when it happens. And so none of those things make it particularly easy to study, and there's a lot that we really just don't know yet about the process of lightning formation, but I think that's what makes it fun. So first of all, the first step that we need in order to get lightning is we need to have charge separation. We need to make one part of the cloud have a different charge from the other. And the way that we do this is that if we have hail and ice crystals within our cloud, then as that hail forms and sort of crashes into another ice crystal, then we get a transfer of charge. That hail tends to become negatively charged, and remember that hail is usually quite a lot bigger. So it's falling through the cloud, and it collides with other things as it goes, and it collects negative charge, and it moves that negative charge to the bottom of the cloud. Those smaller ice crystals aren't quite sort of hail sort of sized yet, end up continuing to move up in their updrafts, and so we end up with positive at the top and negative charge at the bottom. Okay? So, first iClicker question of the day. Given what I just said, what sort of clouds will you not get lightning from? What sort of clouds will you not get lightning from? Okay, let's see how we're doing today. 70% of people are with me. So why will we not get lightning from warm clouds? Yeah, because there's no ice, right? Remember, warm clouds are all above 0 degrees Celsius. So in order to get lightning, we need some part of the cloud at least to be under 0 degrees Celsius. We need there to be ice there. And so we can get lightning from cool clouds, cold clouds. If we get really vertically extensive clouds, like our big thunderstorm clouds, then at least part of those is under 0 degrees Celsius. We have ice, we can get this charge separation going. So let's look at our second step. Our second step is something we call stepped leaders. And what happens is that that charge in the cloud builds up and builds up until we get a quite concentrated part of the air that has a very strong charge. And it's probably only about 10 centimeters sort of diameter. And what happens is that it jumps. That's why it's called stepped. So that charge will build up, and then it'll jump 50 meters or so. Yeah, 50 meters. I was checking it wasn't in feet. So 50 meters, and then that charge builds up again, and then it jumps another 50 meters. But this happens really fast. You don't see it with your naked eye, but this is what's happening as that lightning strike starts, okay? And this is called a runaway breakdown. Okay, don't worry too much about that term, but I would like you to remember stepped leaders. So this is sort of the part coming down from the cloud, and what it does is it sort of branches off, and what it's trying to do is find a path to the ground. It's trying to find that shortest way down to the ground. And then something really weird happens. What we don't tend to see, because it happens very, very quickly, is that we can get things called positive streamers. So as that really strong negative charge gets closer and closer to the ground actually responds. The ground responds by sending up a positive charged streamer instead. And because remember, those unlike charges attract. So that really strong negative charge attracts positive charge from the ground. And when those two meet, we get our lightning stroke. And it actually isn't just one stroke. We get what we call the dart leader, okay? But then actually there's sort of several pulses of charge, of electrons rather, moving from the cloud to the ground, okay? And if you look at the temperature that happens when we get this lightning strike, it's about 30,000 Kelvin. It's 54,000 Fahrenheit. That is extremely, extremely hot, and this is one of the reasons why you don't want to get in the way. And it's all very well to sort of hear about this. Has anyone ever been really close to a lightning strike? Yes? How close were you? A couple of miles? Yeah?
Like 50 feet.
50 feet? Okay, you'll identify with my next video. And warning, bad language if you don't want to hear it. I'll try and cut it off before then. The title might give it away. So I stopped it before the profanity. I know, right? You can always watch it yourself if you particularly want to hear that. But watch what happens. You can see several strokes here. You hear several explosions. Isn't that cool? So you do not want to get that close to a lightning strike. Most of the videos that I show you today are of people that really are in places where they shouldn't be, filming stuff they shouldn't be. So anyway. So now I want to show you something that's a little bit more scientific. With the sort of advent of the much better technology that we have now, we now have super fast cameras that can actually capture all of these stages. So as you watch this video, look for those 4 different stages that we talked about. They can't really show you charge separation, but look for the step leaders. They'll show you some photos of those positive streamers, and then you can see the strokes themselves. So it's sort of a 3-minute video or so, but it's a really cool demonstration of those things we were just talking about. So it's really amazing photography there, and if you are interested, then that is a little clip from something called Raging Planet, and they have a 40-minute section on lightning if you would like to see a little bit more. Okay, so I've just said that mainly what we get is negative lightning strikes. We get negative sort of charge between the cloud, so that bottom part of the cloud is negative and the ground becomes more positive. But what can happen is that if we have strong winds up high in the atmosphere, then that cloud, that nice tall storm cloud that we've developed, gets pushed over. And remember that we've had charge separation. We have that negative charge at the base, the positive charge at the top. So if that top part of the cloud is carried along and sort of lent over further away, then what we now have is this positive charge above the ground. And so what we can get is positive lightning strikes, where instead of having the negative part in the cloud, we have positive charge instead. But really, most of our lightning strikes are negative. And unfortunately, today is not an exciting day for lightning. I had a look before. But there's this little website here, which is really fun, which means that you can watch and see when there are lightning strikes. And you can see that there's the positive and the negative charge. And today is pretty boring, as you can see. There's like a little cluster over here. And when we have big thunderstorms going on around the Midwest, then it is much more fun to look at this. So you can keep that in your sort of mind if you would like. So now I have a little question for you. Where would the safest place to be in the lightning storm? Where would the safest place to be? So let's see how many of you we've killed off. So 5% of people are definitely gone. So let's see what happens to our 5% or so. Okay. So just if I didn't get the point across earlier, this is why you don't stand next to a tree in a thunderstorm. Okay? So for those 5% of you, hopefully you are joking with me, but if not, don't stand under a tree. Top tip. Okay, so how about my other guys? So, we've actually lost the majority of the class, I feel. I only have 39% of my original class left behind. The safest place to be is in your car. So you are fine in a car. The metal of the outside of that car, once that lightning hits it, that charge is distributed around the edge of that car, okay? And then it travels to the ground. So as long as you're inside, it's actually one of the safest places to be, okay? Obviously you want to be inside a house, ideally, but a car would also work. And he even drove that car away, actually, afterwards. So there you go, good electronics in that. So here's my rules for lightning safety, because actually a surprising number of people each year in the US are killed and injured by lightning. And there's some relatively simple rules for what you should do, which none of you know, as you just demonstrated. Okay, so first of all, get inside. So stay off the phone and things that are connected to the electricity in your house, okay? If you can't get inside a house, get inside a car, that will help. If you can't do that, stay away from tall stuff. You saw all of those positive streamers, they tended to be going from the tall things. Those step leaders are trying to find the shortest path to the ground, and that will be through a tall thing often, so like trees, telegraph poles. But, okay, here's the thing. Stay away from open fields, because you don't want to be the tallest thing in the field as well, okay? So there's this what we call the cone of safety. So you don't want to stand under a tree, but standing relatively close to a tree, which is going to be taller than you, is a good thing. If there are no trees, spread out, crouch down, avoid being the tallest thing. If you put your backpack, if you're out in the Sierras or something, if you put your backpack under you, then it will tend to ground through the backpack rather than you, which is a good thing for you. If you hear crackling, if you see a bluish glow, or if you look like that, you are now a positive streamer. Okay, so run away, okay? And these guys, unfortunately, did get hit. They were both okay in the end, but this was up in, I think, near Yosemite or Sequoia National Park, okay? So, yes, it may look fun, no. So, yes? It's not a good idea. Yeah, you want to avoid being in water, ideally, and things that conduct electricity. So, definitely. Okay, So thunder, do you remember when I showed you that video before the profanity and things? Then actually that thunder, when you're really close to a stroke of lightning, it sounds very different. We're used to hearing that sort of gentle rumbling from a distance. When you're right next to that lightning strike, it's pretty damn loud, okay? It's sort of very much sharper, okay? And really that noise that you're hearing is that air, it's moving outwards explosively. It's being heated really fast to a very high amount, and it's sort of producing a sound wave. It's expanding so fast, okay? And so that sound travels out at the speed of sound, which is approximately, for our purposes, 0.2 miles per second. And so most people have done this. If you sit and you count the time between the lightning strike, the flash that you see, and the thunder, you can get a sense of how far away that lightning strike was. So tell me, okay? So remember, I just told you that the speed of sound is 0.2 miles per second. So if you see a flash of lightning and count 10 seconds before you hear the thunder, then how far away was the strike? Okay? So think about it for a second. Consult your neighbor. Okay, so let's take a look and see whether we agree. More or less. Okay, so yeah, so remember, if our speed of sound is 0.2 miles per second, if we have 10 seconds, it's that 0.2 times 10, it's going to be 2 miles, okay? So it's that speed times the amount of time gives you the distance. So now let's talk about thunderstorms, because really our lightning comes from these big storms that develop. So let's talk about how these things form, what they actually consist of. So first of all, we have two types of thunderstorm. We have what we call air mass thunderstorms, which are not gigantic thunderstorms that take up all of an air mass, but they actually are the sort of much calmer variety. They occur within a single air mass. Okay, so they're not occurring at a front or anything else. They're just occurring due to very localized convection within a single air mass. Okay, and we have three stages. We have the developing stage. So for some reason, we have air rising. Most likely it's due to something like localized convection. Okay, so one part of that surface being warmer, that air warms up and rises compared to the rest. And you can see that as that air rises, then as we know, it expands, it cools, we hit saturation, and from that point on we get clouds forming, and that helps that air continue to rise because of the release of that latent heat as we go from water vapor into to liquid droplets. So in that developing stage, we're building our cloud. We're getting this cloud and it's getting taller and taller and taller. And then we get to our mature stage, and you can see that we have that characteristic flat top that we sometimes see, especially if you look out in the desert in the summer, you can often see the flat top. And that's really the boundary between the troposphere and the stratosphere up there. And so this is a really vertically extensive cloud. It's a very, very tall cloud. And you can see that now we've had enough sort of cloud building going on that we've actually formed droplets, hail, precipitation. We've formed big enough pieces of ice or water that it's falling out of the cloud. Okay? So we still have this strong updraft, we still have this strong movement of air up, okay? And that's sort of continuing to build our cloud. But at the same time now, we have precipitation falling out of that cloud. And have you ever stood at the bottom of a waterfall? No? What have you guys been doing? I know it's Southern California, but there are plenty of waterfalls around up in the Sierras. So go and stand at the bottom of a waterfall, or how about a hose or a sprinkler? Yeah, everyone's done that at least. And you feel cold air moving past you, right? That falling of precipitation, it sort of cools that air and it brings it down, okay, with it. So we get this downdraft associated with precipitation. So that's our mature stage. We have both this strong uplift, these strong updrafts still, as well as this downdraft due to precipitation occurring within the cloud. And then as we continue, we get to the dissipating stage. So this is when our thunderstorm is starting to die out. Because at this point, we've built up those droplets so much that we now have precipitation happening along the whole of the bottom of that cloud. Okay? And that has basically blocked off any updrafts. And those updrafts are what was feeding the cloud. It was sort of bringing in nice warm air. It was bringing in sort of new air that could condense out and form cloud droplets. And so if we have downdrafts over the whole base, then we can't do that anymore. And so our cloud is just going to gradually dissipate. Does that make sense? Hopefully. So I have some little notes there. So localized convection, we have unstable air, so that air rises, cools, condenses, water vapor condenses, and we get clouds, and those clouds grow. In this stage, we have precipitation, that can be rain and or hail, and we have lightning and thunder as well at this point, and we have both updrafts feeding the cloud and downdrafts where that precipitation is happening. But finally, our little thunderstorm tends to dissipate, and that's because those downdrafts end up dominating that cloud. And so that really stops those updrafts, it stops that upwards movement, and so our cloud starts to evaporate up high in the atmosphere. Okay. So those were air mass thunderstorms. Those are our nice, gentle ones. We're not too worried about those. But what we are worried about are severe thunderstorms. And these come in 3 different types, okay? So to count as a severe thunderstorm, to make it into that category, then our wind needs to be greater than 58 miles an hour. So that's really very, very fast if you think about how quick that is on the freeway. We have large hail. And do you remember we said that we need really strong updrafts to build bits of hail, because that hail is large enough that it should fall out of the cloud really easily. And so we really need strong updrafts to keep that hail up in the cloud and build it and add layers to it. There may be tornadoes. There aren't tornadoes in every single thunderstorm. They really are a sort of characteristic of very, very severe thunderstorms. They can also be much larger. So our air mass thunderstorms tend to be much smaller. These ones are anything from 10 to 1,000 kilometers wide. So these are much, much bigger systems. They tend to be longer lived. They're around for a bit longer, and they do a lot more damage. This is what people in the sort of central part of the US are more worried about. And in order to build our severe thunderstorms, we need 3 things. We have to have moisture in the air, because without that, we're not going to have clouds, we're not going to have precipitation, and so we're not going to develop our thunderstorm. We need something to uplift it. We need that lifting mechanism, so any of those 4 would do. And then we need something called wind shear. And wind shear is when we have winds in different parts of the atmosphere at different levels going in different directions. So we might have surface winds that are going sort of east to west, but they might meet sort of upper level winds going the other way, or sort of sideways on. And so that's what we call wind shear, and it creates these sort of severe thunderstorms. And so these ones tend to keep themselves going. With the air mass thunderstorm, it sort of killed itself off, right? Because it developed these downdrafts that shut off that sort of upwards sort of updrafts of air. But with severe thunderstorms, what happens is that they become self-perpetuating. The fact that they exist means that we get sort of more thunderstorms occurring. So we'll show you some of that now. So our first type of severe thunderstorm is something called mesoscale convective complexes. Mesoscale just means relatively large. There's a more specific term in the atmosphere for that, but it just means sort of larger scale than our air mass. Convective, there's convection going on, and complexes, basically groups of these big sort of severe thunderstorms. And they look fairly blobby. Okay, so here's sort of a little image of sort of what these things look like, and those bright colors there represent little individual thunderstorms. So let's think about how they form and how they keep themselves going. Why don't these ones die out like our little air mass ones did? So I want you to look at my little 3 diagrams here. So first of all, we're going to start at the top. So this is our initial time. So at this sort of time 0 almost, we have 3 different thunderstorm cells, okay? 3 little different thunderstorms. So this first one is dissipating. It's starting to die out, just like our air mass did, because we have precipitation, and so downdrafts dominating the bottom of that cloud. Cell 2, we still have a little bit of updraft, but we also have a downdraft. So this is our sort of mature stage. And then cell 3, this is our cumulus stage. This is our sort of beginning of our new thunderstorm cell. And you can see that part of the reason that this new thunderstorm cell is forming is that the downdraft from cell 2, that downwards cold air, hits the ground and it spreads out in both directions. And so as it spreads out in both directions, it's basically sliding underneath the nice warm moist air, and it forces it up. So the presence of this cell, cell 2, and the presence of that downdraft means that we grow this third one ahead of that. Does that make sense? Yeah? So if we look 10 minutes later, we can see that now cell 2 is dissipating. We have precipitation over the base of that. But cell 3 has strengthened from that cumulus stage it was before to now again being a mature thunderstorm. And so now it has downdrafts as well as the downdrafts from our old sort of cell 2. And so that sort of cold front almost, that cold air that's spreading out at the surface that's forcing up our warm air either side is sort of moving along. And so if this is sort of forcing cold air this way, we force more warm air up. We start to form another new cell. And again, over time, cell 3 will become a sort of dissipating stage, but we still have these downdrafts. It's still forcing that cold air forwards, and it's still forcing warm air to rise. So once we have these things, they tend to keep themselves going. And they can travel for sort of hours, if not a couple of days sometimes, across the US. And they tend to go from our side on the west towards the east. So that's our mesoscale convective processes, and these are the blobs, okay? There's no better way of saying it. It's blobby. This one is our squall line thunderstorms. This is our second type of severe thunderstorm. And these are lines. So instead of blobs, we have lines. And these tend to form ahead in that sort of warm part of the mid-latitude cyclones. So they form ahead of that cold front, which is sort of trying to catch up with our warm front. Okay? So here's an example moving through Texas. Okay, you can see that nice line of that really bright color representing where we have the strongest activity. And so why did these form? So they originally actually form just ahead of the cold front, but then they move much faster, so they end up quite a lot ahead of that cold front, in the middle of that nice warm air. And so these are bands. They can be up to sort of 500 kilometers long, so they're really very large systems, and they sort of sit that 300 to 500 kilometers ahead of that cold front as it moves across the country. Okay? And remember, we have that nice warm air in the middle, which is going to be easy to lift and to make rise. So now let's look at this type of thunderstorm, and you can see that now you can really see again where that downdraft from part of the thunderstorm is playing a really important role in forcing the air ahead of it to rise. So if you look, the direction of my thunderstorm is the other direction from the other one. It's going in this direction. And so what happens is that this cold air, as it sort of moves down, as we get precipitation and downdrafts, it hits the ground, it spreads out in both directions. And in this case, it spreads in the direction of that nice warm air that's in our nice sort of warm part of our mid-latitude cyclone. And it forces that warm air up. And so that warm air goes up and it rises and it forms new parts of the cloud. Okay? And so that sort of the existence of these downdrafts ends up creating more of that storm. And so as this moves along, then this gust front, this sort of cold air, also moves along, and we develop more and more thunderstorms, and we move in the same direction. And then lastly, we have the supercells. So these are the fun ones. Not if you're living near them, but they're very amazing things. So these are smaller than those others. They're 20 to sort of 50 kilometer, but instead of those others, which are lots of little thunderstorms, this is one gigantic thunderstorm cell. Okay? And the thing that characterizes this is that it rotates. It has this large-scale rotation going on, and so this type in particular are very sort of likely to spawn these big tornadoes. If we have tornadoes, this is where they tend to be. And so you can see that in some ways it looks quite similar to what we just looked at in terms of the score line. We have these downdrafts, and we create this sort of this gust front, this cold air that moves into the warm air, forces that warm air up, and sort of keeps itself going. And we get this sort of beautiful cloud forming. We get something we call a shelf cloud. You can also see that where that cold air is moving in one direction, the warm air on the top is moving the other. And it creates this really weird thing called a roll cloud, and I'll show you an example of one of those in a second. But the thing that makes it rotate is that we have different winds going in different directions at the different levels, okay? So in the middle level, we have winds traveling in one direction. In the lower level, we have them going in a different direction. And so we end up with this big, large-scale rotation going on. So this is our supercell thunderstorms, and they're incredibly beautiful, and they're incredibly destructive. They're very, very intense storms. And this is what you see. If you look at a weather radar, remember, these radars, they basically beam out pulses of radio waves, and they wait, and they hear the response, the reflection back of the things like in the atmosphere, things like cloud droplets or rain droplets. And this is the signal that you get when you get a severe supercell thunderstorm. You get this really strange hook shape, okay? So the redder the colors, the more intense the precipitation, the more intense the activity there. And you can see that when you get this hook shape, you know that there's a severe supercell thunderstorm on the way. And you can see another one up here, another one down here. So this little hook is basically where you could see that air coming in and starting to form that cloud. So we'll come back to why that's important in a second. So the other thing that's associated with thunderstorms that we don't hear as much about are microbursts or downbursts. So we get this really intense uplift going into a storm, but we also get these really strong downdrafts. And when I say really strong, they can be up to 165 miles an hour. That's easily hurricane force winds. So these are really intensive winds that they can do a lot of damage, especially if you're a farmer and you have crops in the fields. And we also get these downbursts, these downdrafts, with diameters less than 4 kilometers. And when we get those, we call them microbursts, okay? So here's a question for you. You've ever been stuck at Dallas or somewhere in the Midwest? Thunderstorms and airplanes don't mix terribly well. So what do you think is the most dangerous aspect of a thunderstorm for an aeroplane? What would you not want to mix with an aeroplane? So you may have got a clue because I just talked about it, but yes, you are right. These 44% of people would be right. Okay, so for those of you, again, that don't believe me, you can watch a plane getting struck by lightning and it's fine, okay? So there's a little video there of a plane being struck by lightning. I think it was prepared to make people feel better about flying, so it's got very calming music over the background. But really the most dangerous thing is the microburst. If you're in a plane and you get caught in an updraft, it's not the end of the world, you're going up, okay? What you don't want to be caught in a plane is something very rapidly moving you towards the ground, okay? And that's what those microbursts can do. So in particular, the reason that you are stuck at an airport when we have these thunderstorms going on is because when you're taking off and sort of landing, you really want to have a pretty good idea of how fast you're going and the rate of change in terms of altitude. And those strong winds make it really hard to do that. Because if you imagine, if my plane is sort of approaching the airport, it's getting lower, but as it approaches, it's encountering this strong wind, this strong headwind, and so it has to power up to get through that headwind. But on a very small scale, like on that microburst scale, on that 4-kilometer scale, as it comes out the other side, all of a sudden, it's going to shoot forward really fast, because now instead of having a headwind acting against it, it now has a tailwind. And that makes it very difficult to control the altitude and the speed of the plane, and you really want to have both of those under control if you're going to be landing, okay? So those are why thunderstorms tend to ground our aircraft. So now let's think about tornadoes. Has anyone ever experienced a tornado? Really? Where were you?
Alabama.
Alabama? How big a tornado was it?
I
pretty big, big enough, right? Anyone else? Yeah, how big was your tornado?
Well, I'm from Oklahoma City, so
Oh. Yes, absolutely. So you're an expert. You should be giving this rather than me, I imagine. So absolutely. So Oklahoma City, and I just showed you the map, right, of that supercell sat right on top of Oklahoma City. So we're going to talk about tornadoes, and these are incredibly dangerous things. They really do kill people every year, but again, they are these amazing, beautiful, spectacular, powerful pieces of our atmosphere, and I love them. Okay. So what do we need to make a tornado? What ingredients do we have to have for a tornado to form? So you can see that we have quite specific conditions that we need, but really the northern US is perfect for these conditions. So what do we need? We need to mix warm, moist air, okay, with colder, drier air. And it's pretty easy to do that in the center of the US here, the part we call Tornado Alley, because we have cold, dry air that sort of can come down from over sort of Canada and the US, and it can meet lovely warm, moist air that's coming off the Gulf of Mexico here. And so what happens is that where they meet, they're moving in different directions, and we get really unstable air, so we sort of can form these tornadoes. And you can see that for this to happen, we tend to need a nice big bend in our polar front. We need sort of nice upper level winds that match that. So I want to show you a bit of an example from last year, exactly to the day, 20th of May 2013. And you can see that this map shows the upper level winds, the jet stream winds quite high up. You can see there's a big loop occurring over the US at that time. Okay? And so if we want to think about cold, dry air moving south, warm, moist air moving north, if we look at the winds for that day at the surface, you can see we have cold winds coming from up here, meeting nice warm winds coming from up here. Okay? And so it's sort of meeting in this, again, this is what we call Tornado Alley, this area where we get really a lot of tornadoes forming. So the second thing we need for a tornado is wind shear. So we need those winds traveling in different directions because we need to create this rotation. And you saw that in the supercell. And also we said that, remember, ahead of that supercell, we get this roll cloud developing. And these roll clouds are also incredibly beautiful. And I love this one. This isn't part of a thunderstorm system, but it's a really spectacular video showing this really weird cloud. It's called a roll cloud that can form. Oh, there's people. But this is a pretty extensive cloud. And if you watch carefully, you can see it spinning and rotating. Isn't that cool? And it's created because of the wind shear. We have two different wind directions going on, and it's created this enormous cloud that really goes right across the horizon, which is really fun. So you can take your time and look at that another time. The third thing that we need is CAPE. So what does CAPE stand for? It's convective available potential energy. So what this is basically just a measure of how unstable the air is. We talked about whether air was stable, conditionally unstable, or absolutely unstable. Have I got the right ones there? And so what CAPE is just a measure of that. It's quantifying how unstable that air is. And we need that air to be unstable. We want it to rise. We want it to create these big thunderstorms. So if we have all of these things, we have that mixing of warm, moist air. It causes uplift and cloud formation where they meet. We need that wind shear, creates a horizontal vortex, just like we saw in that video, and it can become lifted. And then we also want this sort of a large amount of instability. We want air to be unstable because that helps us create these updrafts that can extend and intensify. And so all of these are somewhat interrelated, but without all of these, you don't get tornadoes forming. So let's look at my roll cloud again. Let's think about that horizontal vortex that we're creating. It doesn't need to be a cloud. It can just be that the air is moving that way. We might not see it necessarily. And you can see what happens if I take this horizontal vortex, this horizontal spinning air that I've created, and then we have an uplift. We have sort of an updraft come up and lift that. Okay? So what we're showing here is in that sort of ghost type image, that what that horizontal roll cloud used to be, and now we've seen an updraft, and that basically lifts that central part of that sort of rolling vortex. And now we have a part that is going up into the cloud, and we also have a part that's going down. And it's this rising section here, this part that's going upwards into the cloud, that's how we can form our tornadoes. And this other side is sort of a strong downdraft, okay? And so where we tend to get these is ahead of that rain. So here we have these downdrafts, we have heavy rain, but behind that, where we have this updraft feeding into our cloud, bringing in more warm, moist air to sort of rise and sort of cool and condense and form clouds. This is where we can have this really strong updraft happening, and that's if we basically stretch that updraft enough, then we can get that vortex to extend down from the cloud and actually hit the ground right there. And so this is why often these storms are quite dangerous, because often you can't see the tornado through the precipitation, that really quite heavy hail and rainfall that you might have on one side, okay? So that's why these things are a little bit dangerous. And this is coming back to this Oklahoma City image and sort of supercells in general. Where these tornadoes tend to be is here, okay? Right on this side of the hook. So if you're somewhere where they experience extreme weather and you can see one of these things coming towards you, this is the area that you really want to be very concerned about, because this is the area where that tornado is likely to be forming. And so let's take a look at where tornadoes form. So you can see that the US is actually the main place in the world where we see these. It isn't just that we're recording more of them. We just happen to have that right atmospheric conditions occurring over North America for us to form these tornadoes. So we do get them on every single continent. They've been observed everywhere apart from Antarctica, but North America in particular is very severely affected by tornadoes. And in particular, that tornado alley up through Texas, through Oklahoma, Kansas, they really do get hit hard by tornadoes. We get very, very many more of those, whereas if you look, we don't really have much chance where we are to get a tornado. We get a tiny one every now and again, and it certainly doesn't usually have the potential to become particularly large, okay? So how do we measure tornado strength? We use the Fujita scale. It's sometimes called the enhanced Fujita scale, which might put an E in front of that F, okay? And you can see that F0 is basically our very gentle tornadoes, if you can call any tornado gentle. It's got the lowest wind speed. It's sort of 40 to 72 miles an hour. It might do some damage to sort of loose chimneys or tiles on your roof. It might blow off a few leaves, but really it's not going to do very much damage, okay? As we move on up, by the time we get to, say, F3s, now we're talking about wind speeds of about 160 to 200 miles an hour. You are not going to be standing up in that, okay? So it's very, very, very strong winds. But remember, it's very localized to just around that tornado. And then you're sort of talking about really demolishing quite well-constructed bits of your structure and sort of doing some real damage. And then we move up to F4s, F5s. F6, I don't even know why they included F6 on here, because there are no F6s as far as I can tell. I don't think we've ever recorded an F6. F5, we do have, and we have seen several in the US in the past few years. They're less than 1% of the tornadoes that form. You can see that really most of the tornadoes that form are these F1s. And as we get higher and higher in intensity, fortunately for us, they become very much less common. But with an F5, there's very little left standing. I'll show you a video in a second. But even really very well-built houses with foundations are just leveled. There really is very little left in these things. And these particular tornadoes, unless you have a storm sort of shelter, can be incredibly devastating. And this is where we lose lives, unfortunately. So let's go back to this day 1 year ago, because we had a very strong F5 tornado that hit Moore, and it unfortunately caused, I think, 24 fatalities, and it injured 300 and something people. And so here you can see that over this particular area, you can see that there's this sort of little area of bright sort of reds and oranges and yellows. So if we zoom in on that, again, we're at Oklahoma City, central place for all of these things. And you can see that we have this classic hook type shape. to our storm cell. This is a supercell thunderstorm again. And in particular, this area here, a lot of the bounce back of the radar there isn't actually from droplets of moisture in the air. That's from debris. That's from stuff that's being forced into the atmosphere by this tornado. That's actually just a debris ball that's casting the reflections there. So this is an extremely strong tornado. And unfortunately for more, it sort of almost duplicated the path exactly of the 1999 tornado that also came through. So you can see there's a green track on there, and there's also a red track. And you can see how close they are, and it's not for any particular scientific reason. It's completely chance, but they were extremely unlucky. And so I wanted to give you a sense of what this tornado looked like. And so here's a time lapse taken from a helicopter, so it's not going as fast as this. They do go at something like 60, 70 miles an hour. You are not outrunning one of these. But you can see how wide this got. You can see how much debris is getting pulled up and scattered. And so let's keep an eye on this and see how it comes through. So you can see that rotation of the storm as well as it comes across. But the nice thing about tornadoes is that they don't tend to last very long. So they tend to travel in quite straight paths. You can see that this one isn't winding around that much. It goes in a pretty straight line very often, and they don't tend to be on the ground for more than a few tens of minutes. A couple of them might last a little bit longer, but they tend to be quite short-lived. And they also don't stay the same size the whole time. You can see it's starting to weaken now. And in a second, you'll see it just sort of dissipate completely. So it can both weaken it and it can strengthen again. And so it's a constantly changing feature in the atmosphere. And you can see how easy it is to miss that. If it's shrouded in rain, you can't necessarily see terribly well that it's coming towards you. And there it goes, just dissipates. So that was the Moore tornado, and unfortunately it did an awful lot of damage. So let's take a quick look at what you should do. So today is really safety day. So now you know what to do in a lightning storm. So now, tips for tornado shelter, okay, or to tornado survival. So first of all, you do not want to be outside again. Try to get to a storm shelter or a basement. If it's a strong tornado, it's going to really do a huge amount of damage. If you don't have one of those, try to find an interior room that's really very solidly built, or some sort of cupboard. Try and get away from windows because they will likely smash and you don't want to be covered with glass. Bathrooms tend to be really very good for that. Cover yourself with something because there's going to be a lot of flying debris, and that's when it's carried by these really strong winds, can also do you some damage. So things like a mattress over the top of you will really help you out in that case. If you are in your car, do not try to outrun the tornado. Please sort of just get out and where you can, lie down in the ditch. Okay? What you're trying to do is get flat so that no air can get underneath you and carry you. Okay? You want to be flat to the ground as much as possible. And one of the biggest misconceptions about tornadoes is that you are safer if you hide under an overpass. That is absolutely not true. It's this complete myth because a film crew happened to run and think they were safer and hide under an overpass, and it got broadcast and everyone thought that was the good thing to do. Being under an overpass actually channels those winds through. Okay? So really you don't want to be under an overpass. You want to be flat and low ideally. So lastly, I wanted to show you a couple of the really big tornadoes that we've had in the last couple of years, and in particular 2 from 2011 that were incredibly damaging and very sad occasions. So again, you can see the radar for both of these. You can see the little hooks that form, and so you can see where the tornado is. And in both of these cases, again, some of that radar bounce back is most likely to be some sort of debris. So this was in Tuscaloosa. It was an EF4, but it was a huge tornado. It was 1.5 miles wide. caused 64 deaths, $2.2 billion in damage. There are 2 videos there, shot again by people that really shouldn't have been out filming a very large tornado coming towards them. Please don't pack up just yet. And lastly, we have Joplin, which was an incredibly damaging tornado. It was an EF5, a really strong tornado. It was 1 mile wide. It caused 161 deaths and $2.8 million of damage. And I'm not going to show you all of these, but if you are interested, then there's some very, very intense videos. So here's a guy who was sheltering with a bunch of people. I'm not sure you can see it terribly well because it's very dark, but he's sheltering in a gas station. And there's a whole bunch of people that have stopped and taken shelter. And you can see how dark it is outside as this tornado approaches. And as the tornado approaches, unfortunately, all the windows blow in, and so they run into a back storeroom and they hide with everybody. But watching it, it's a very intense experience because you really get a sense of how terrifying this is, and how chaotic and how loud these things are as well. And I then wanted to show you, these people were very lucky. They were in that Joplin tornado and they survived. But this guy shows you where they climbed out of, and I think this is a good point to show you exactly how much damage these EF5s can do. So this is the gas station where they were. So I'll jump forward to the bit where he shows you where he climbed out with everybody else. There are about 20 of them perhaps that climbed out and were very lucky to have escaped. There is nothing left there. And this is why it's such a dangerous thing. This is a good idea why you should know what to do in a tornado. Okay, thanks guys. On to hurricanes on Thursday.